All right, everybody, we're going to talk about some electron configuration stuff today. So let's see how this goes. So Pauli stated that all electrons have a unique set of quantum numbers, and this is a solution to the wave function for that electron. This is the function, or function is probably the best word. This is a function that is based on the four quantum numbers n, l, ml, and ms. And these four quantum numbers will tell you exactly where the electron is and what area that electron takes up. What kind of wave does the electron have? Three-dimensional wave with shape. So, for example, if we're talking about the 6 electrons on carbon, then we know that some of those electrons are going to be, say, in the 0, n equals 0. This is going to be n is 0. And then if n is 0, the only L value that's allowed is another 0. And that also means that the only ML value is 0. And then we have the allowed values of negative 1/2 for our MS, or positive 1/2. So our second electron is going to have the same values. And then we go to the next shell. So both of these electrons have n, oops, I just realized a mistake, didn't I? N doesn't start at 0, it starts at 1. I feel like I keep making that mistake. Okay. So n starts at 1. So for n equals 1, both of these electrons have L equals 0 or S. And there are two of them. So this is a 1s2 configuration for these first two electrons. But of course there are 6 electrons, so we go to the next shell and we start with our lowest L value, our lowest magnetic number, or lowest, whatever we called it, the lowest orbital shape value. And then if L is 0, then the only value for ML allowed is 0. And that allows us to just choose one of our angles, one of our spins. And we can repeat this process without changing orbitals. And this creates our 2s orbital, 2s2. And then here we don't have to change energy levels, but we can increase energy by going to the next value for L. And that allows us some more options for ML. We can now go from -1 all the way up to +1. I'm going to start with the lowest number, and we're going to explain why that is in a second. And then we're going to go the same route, but now increase our value to 0, and then change. We're always going to change that spin number last. And so this gives us our 2p4. 2p2. Thank you. And so this combination of quantum numbers can be best represented, or one representation would be just to lay out these labels, and we could call this 1s2, 2s2, 2p2. So we're just organizing these quantum numbers into a representation that is a little easier to type and a little easier to interpret. We did lose some information. Notice we lost the spin up, spin down information. So we don't actually know what the spins are of these electrons. We just know where they are. So this is called an electron configuration. It's a useful tool for looking at elements and thinking about why they might be reactive, or what type of reactivity they might have, and what sort of chemical bonding they can make, and all sorts of things like that. So for example, later on, possibly you've covered double bonds at some point in your life, maybe in an organic, the organic section of grade 11, and you might have talked about something like carbon dioxide. So carbon dioxide is drawn this way. It has 2 double bonds. These double bonds are a direct result of these p electrons. So these p electrons, if they did not exist, we could not form double bonds. And in fact, only elements that have p orbitals typically can form double bonds. So none of the metals really form double bonds very easily. That's not entirely true. It does happen, but not easily. Usually the double bond formed with a metal requires something like a non-metal that has that has p orbitals. Okay, so how do we do this? How do we figure out these configurations? Well, another factor of this is that since every element on our periodic table has a unique number of electrons, they all are going to have unique electron configurations. So there's a couple options here. I'm going to go through a couple of them. The very worst option, I think, is that instead of learning any of these rules and any of this way to do it, you could theoretically memorize the periodic table, memorize all of the electron configurations or a large portion of them, or you can look them up. I mean, these are electron configurations are known. You can just look them up. They show up on Wikipedia under the entries for elements. So there are electron configurations available just to look up. But I want you to try to think about some of the rules and the ideas about these quantum numbers and what they mean to kind of interpret why the electron configurations are the way they are. I'm always interested more in if you can determine why something is more than if you can do it. If you come up to me and you say, "Hey, John, I can do the vanadium electron configuration. Look, I'm doing it right now." That's great. I'm really proud of you. But if you can tell me why the vanadium configuration and the chromium configurations are so much different, that's when I'm starting to get excited. Okay. So some things to think about. I always think about energy. So why does it go in this order? Why is it 1, then 2, and 0, then 1 for these electrons? Why did it go that way? Well, think about it like when we were drawing these pictures. So if we were talking about n equals 1, right? N equals 1, L equals 0. We're talking about a very basic shape, very small. So in this case, the positive nucleus and the negative of the electron are very close together. So the force between them, the force of attraction, is strong, right? The Coulomb force, or whatever, the Coulomb attraction between that electron and the proton is the proton core is very strong. If you go up to the next solution, up to n equals 2, you're essentially going to be increasing the radius. Okay. You still have that little tiny proton, exactly the same size proton, but now R has gotten bigger, right? R increased. So if this is an increase in R, increase in R. So an increase in R means that the force goes down. And so now the distance between the electric charge and the charges has been decreased. So by Coulomb's law, our force equals kQq over R squared. We've lost some energy. We've lost some force. So these electrons can be thought of as more energetic. They now have less attraction to the nucleus, so they're more energetic. They're more free to move. The energy hasn't disappeared. It's now been converted into sort of active energy or something like that. And that's not a perfect analogy. It's probably not entirely correct either, but it's a good way of thinking about it. Like now there's a looser connection, so that electron is more active, more energetic, ready to do more chemistry. If you go to the next example, where you have, this is L equals 0, if you go to n equals 2, but L equals 1, then I actually have to be a little bit careful, because what I'm going to do is I'm going to take a duplicate. Whoa, don't do that. Okay, and I'm going to move this duplicate over. No, it's not what I want to do. Okay. Okay, duplicate. No, delete. This one, duplicate. Okay, that one's easy to move. All right, so for this next one, we actually are going to switch to the pi orbital, right? And the p orbital has this sort of double thing, but the overall size of it is exactly the same. So we can kind of think that the distance here is the same. R is about the same as previous, but shape is more complicated. And so in this way, the more complicated shape means that the overall trend here has been towards a higher energy, right? Higher energy. And we saw the sort of the Hund's filling diagram, the energy diagram in class, and I'll probably flip to that in the next section. But that's the idea. So the energy is higher, the higher and higher energy as you increase N. While you've increased N, if you increase L, then you increase the energy as well. If you increase N again, then you'll have even more options. You'll have L equals 1, L equals 2, L equals 3. And so we saw this diagram in class, and we can kind of draw it out. First, you have 1s, right? This is N equals 1, L equals 0. And then up above it would be 2s, or N equals 2, L equals 0. So we got an increase from L going up. But then if you increase L but keep N the same, N equals 2, L equals 1, you also get an increase, and that's our 2p orbital. From here, you can also see an increase if you just go, so this is the increase from N, this is N's effect, N, and this is L. So over here we have our 3s, and then we're going to have an L effect this way to a 3p, and then we're going to have another L effect to the 3D, right? This is our N equals 3, L equals 2 now. At the same time, you can do a little bump here, and you from your another N and get up to a get up towards the N equals 4, and this is our 4s orbital here. And I didn't do it quite in the right spot. Okay. And this is where it gets a little tricky, because the jumps from N are not super huge. So this 4s orbital is actually a little bit lower in terms of energy than the d orbital, and that's where we're going to have this interesting filling that we've been doing in class. Okay, so here's the rules. Aufbau says that the ground state electron configuration arranges the electrons such that the lowest energy subshells and orbitals are filled first, and the higher energy ones are empty. So if we look at this diagram, we have to fill in the order of lowest to highest. So 1, 2, 3, 4, 5, 6, and this one is a p orbital, so we actually end up with, we should probably draw in all 3 of them. 3, and there's 3 here, and then there's 4, 5 of them, so it's really big. That's 6, okay. So as you go up, we've got increasing energy. Boom. And this is your MLs down here. This is -1, 0, 1. This is going to be -2, -1, 0, 1, and 2. Okay. Then we have Hund's rule, where the degenerate orbitals, those with subshells with different ML but the same L, the subshell must be half filled first before the electrons are paired. So maybe I do need that energy diagram. Let me see if I can just find an energy orbital energy diagram. And I can see one here that someone drew. Oh, I like this one. How about this one? That one looks okay. Let's see if we can get that. Oh, that's a little nicer. Delete. Okay, so I'm just going to drop that down. Oh yeah, nice and clean. Okay, so this is a great look example. Here they've even drawn out the nucleus, and we can kind of think that these energies are related to the R. And, so this is a higher R, really far R. So R is increasing as we get up in energy. Those are all proportional ideas here. So in this example, we have to, let's do something like, let's do vanadium. Which means I'm going to have to remind myself how many electrons vanadium has. Vanadium, which is 23, so 23 electrons. We have to go by Aufbau principle. Ground state configuration arranges electrons first. So let's go 2 electrons down there. That's the lowest one. 2 electrons, so we're up to 4. And then we need to start filling this next one, but Hund's rule says that these are degenerate orbitals. Notice they're all on the same line. So I need to try to fill them halfway first. So 1, 2, 3. Okay, how many am I at? I'm only at 7 right now. So 8, 9, 10. And then I go up by off bow. I go up to the next orbital. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then there is a little tiny increase to the 3D, but this is, off-bow said that we have to go up by the orbital energies. So the next orbital energy is 3D. And I'm up to, oh boy, I've lost track here. I believe this is 18, 19, 20. So I have 3 more electrons, 21, 22, 23. Those are, I haven't broken any rules. Hund's rule says that the subshells must be half filled first before electrons become paired. Now let's just double check my poly. Did I put more than 2 electrons in any orbital? No, I did not. So that would be the filling. And this is the energy diagram filling. And I like this a lot, but I will show you the zipper method in 1 second. Okay, so let's do the zipper method. I think this is kind of the primary method that a lot of students will use because it's just easier. You can set up one of these little charts very easily. You just start typing. Well, not on an exam, obviously. You're probably going to write it. But if you just start labeling things this way, you can use like one line of line paper, or if you ask for a little extra piece of paper on an exam, and you can just type this. So this is pretty easy to type, I think. You can even go all the way out to G if that makes you feel more comfortable, which you'll never use, but if you wanted to put a 5G out there, that's fine. And what you do is you do this sort of zigzag. So you fill in this order. You fill the s orbital first, then you go back, you fill the next s orbital, then you go back and you fill the 2p orbital, then you go to 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and then 4f, 5d, something like that. So let's just do an example. So if we were going to do vanadium again, let's just do vanadium again. With this method, we would go 1, 2. Let's draw this pattern here. I think that's good. That's good enough. So we go 2, 4, then I go back up to here. 4, I can put up to 6 in a P. So 4, 10, 12, go back up. 12, 18, 20, and then from here you go all the way back to here, 20, and then there's my last 3. So then I just add them up together. 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, 3d3. Now in this example, actually, there's something I do like about this organization, is that if I was reading this, I would read it from left to right after I'd filled in the diagram, and I would probably write it as 1s2, 2s2, 2p6, 3s2, 3p6, and I'm reading left to right, 3d3, and 4s2, and this would actually be the reactive one. This is the orbital that's most reactive, because it's the largest. N equals 4. And so that, to me, this is actually a nice organization. I kind of like to see the ends organize things, even though we fill in a different orbital in a different way. And this does produce a this weird orbital that's got only 3 electrons in it, but it's lower. I don't care as long as the numbers are right. It's all good, but it is kind of fun to have them organized in the physical way, thinking about this as the outside of the electron of the atom. So again, let's do a little bit of thought experiment here. What we have is we have a nucleus, right? We have let's play a little around with colors. We've got 2 electrons here. Then we have another sort of shell, and that shell is your 2p shell, and that 2p shell has 8 electrons. So maybe I'm going to get in here. I've got 2 electrons, the equivalent of 2. I've got sort of 2 and 6, 2 plus 6 in that next shell. Then we have another shell on top of that. I love a blue. This shell is the 3 shell, right? N equals 3, so that's on the outside. It's the electrons in this shell are in all sorts of weird shapes, but we get 2 electrons there. We have 2 in the s electrons. We have 6 p electrons, and we have 3 d electrons. 6 plus. And so those are all at about that distance. And then on the very, very tip of this thing, we also have one last little bit of electrons right along the outside, all at the same distance. It doesn't actually matter, wouldn't matter if it was in the S or the P or the D. It would all be the same distance away. And there's these 2 extra electrons on the outside. So when we think about this atom coming into contact with stuff, if we think about this is a vanadium atom, it's floating around and it comes into contact with an oxygen, what is that oxygen going to be bouncing into? It's going to be bouncing into this 4s orbital, because that's 4, right? This is n equals 4. N equals 4. We had our blue one was n equals 3. We have our purple one, which was n equals 2, and we have our green one, which was our n equals 1. So the outside orbital, that n equals 4, this is why n is the most important. It's the principal quantum number. So anyways, so this method, it's all about memorizing the zigzag. You just type out this, or you write out this little key on your paper. Most of the time, you're not even going to do anything that's as big as an f orbital. And then you just figure out how to do a zigzag. If you can figure out the order of filling using that zigzag, you are good to go. Okay. Now the next method is what I use, and that is the periodic table method. So the periodic table is built around the electron filling. The electron configurations are consistent down a group for the most part. So what you can do is you can count 1, 2, 3, 4, 5, 6, 7, and this will tell you the shell of any element in that row for their s orbitals. So this and their p orbitals. So period number equals the largest n for s and p orbitals. So in this way, I can just kind of close my eyes and pick a number, and I can say, okay, barium, right? So barium, example barium, it's in the 6th row, 6th period. Therefore, n equals 6 is the max electron. So n equals 6 is going to be the largest electron on there. Then the other piece is to divide this thing up into groups. So you have your S group, you have your D group, and this periodic table is just nicely organized for us. And then you have your P group. And down here you even have your F group. So this is F. So the group dictates which orbital was filled last. And may be partially full. And so in this case, we go, so in barium is in s orbital. So barium's right here. It's in the s group. So we would be talking about a 6s orbital. This is the largest orbital, the last orbital to be filled. So from my, from my previous example, I would actually be looking at putting in a 6s down here, and I would know this is where I'm going to stop. And then that means I just have to fill in anything that's less than an S6. You do have to kind of know your organization, but you can even cheat a little bit more, and you can actually, if you can map out this in your brain, I can just start walking towards barium from the top. So I count along the periods to figure out how many electrons in all overall. So looking here, I see this 1s up here. So barium's way down here. So I definitely have 1s2. I definitely have 2s2. I definitely have 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and 4d10, and 5p6, and 6s. And this is the only one that's in question, but we notice that it's the second element of that row, so that would be s2. And we could also add up all the electrons and figure it out. So for barium, we would go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and 5p6, and 6s2. Okay, so let's try that again and see if we can figure it out. So I'm just going to try copying this to a different page. Okay, so let's just paste that thing down. Oops, and let's clear out some of this nonsense that we've got going on here. Okay. All right, so that's clear. So let's do another example. Let's do something a little bit easier to count. So I'm going to start with, let's do a gallium, for example. So gallium is right here. So from this, I can look at the row 1, 2, 3, 4. So fourth row. So that means that I'm going to have n equals 4 at some point. And it's in the p block, So I also am going to have a 4p orbital. And I don't know how many electrons it is, except we can kind of make some assumptions here. We can get really close in here. We can go, this is going to be p1, p2, p3, p4, p5, p6, because there are 6 electrons across the top, or 6 spaces in this group. So there are going to be up to 6 electrons in that p orbital. We can do the same thing over here with s. These are all s1, these are all s2. Of course, helium is special. It's 1s2. It's just been put over on the other side. And then we also could even do something like this. D1, D2, D3. I'm going to skip this one. D5, D6, D7, D8. Those of you who are in class will know why I'm skipping these weird ones. D10. And these are weird. These are special. And so these general counts will help you out. And all I'm doing is I'm going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wherever it lands in the group, that's how many electrons are in that type of orbital. So D group, If it's the 10th element in the D block, so like zinc, then it's got 10 electrons in D. If it's the third element in the P block, like nitrogen, then it would be 1, 2, 3. That means it has 3 electrons in the p orbital. Gallium is in the first of the p, so we're talking about 4p1. And then you just start walking backwards. Okay, so if it's 4p1, then it means it has all of its d electrons. According to this rule, it should be 3 d electrons, because d electrons always start one less. It means it also has all of its 4s electrons, because it's past calcium, so it has 4s2. It means it's past argon, so it has all of its 3p electrons, so it's got 6. It's got all of its 3s electrons, that's 2. It's got all of its 2p electrons, that's 6. It's got all of its 2s electrons, that's 2. And it's finally, of course, way past its 1s, so it has all of its 1s electrons, that's 1s2. So that system works too. This is probably how I do it in my head. I have this all mapped out in my head so that I when I look at the periodic table, the first thing I do when a student asks me about a certain configuration is I look at the table and I go, okay, which block are we talking about? So let's pick another one. Let's pick zirconium. So zirconium is right here in this block here. So this one is in the 5th row, but it's in the D block. And notice that the D block is always one less than the row. So I guess we can write that D orbitals are always one less than period number. Okay, so zirconium's right here. It's in the 5th row. So 5th row. So there is going to be an n equals 5, but it's in the D block, and it's in the D block or D group. So partially filled d orbital. If you combine these two facts together, then you'll say that it's partially filled 4d orbital. And then it is the second D metal. So that implies that it's not just 4D, it's 4D2. Whew. Okay, so now we know what the last electron is. If it's 4D2, and we do know that there's n equals 5, so I'm still missing something, so I got to put that 5s2, and then everything else is filled. I don't even have to really think about it. Okay, well, I'm starting at 4. So I'm going to go, if this is 4D, then that means I have to have a 4P, I have to have a 4S, I have to have a 3D, I have to have a 3P, I have to have a 3S, I have to have a 2P, and I have to have a 2S, and I have to have a 1S. And they're all full. This is the only one that's not full. Not full. Everything else is full, so I just have to know that P's have 6, S's have 2, D's have 10, P's have 6, S's have 2, P's have 6, S's have 2, S's have 2. Does the order matter? No. Order doesn't matter. Right? I don't even like this order. I would rather see something different. I would rather see the 5s put on the right. But you know, it doesn't matter. As long as you have the right electron number, that's all that matters here. 5s2, something like that. And so that's the case. Okay, well, I did skip some elements tonight. So this is the last thing, the last thing. So if you need to, just stop here for a second and go back and do some electron configurations. Pick anything that's not chromium, molybdenum, tungsten, or zinc, or sorry, chromium, silver, and gold. Do like 5 of them. And you know, so if you need some suggestions, do sulfur, do phosphorus, do selenium. Try out try out ruthenium. You know, do an element you never heard of before. Maybe not do F block, those are weird. Niobium, I used to love niobium. Very cool element. So do these 5 and see how it goes. Look up the answers on Wikipedia. You can just type the element, it'll give you electron configuration. You can go to a website called Web Elements, is also very cool. Web Elements. It's a periodic table of elements. It's very interactive, and they have electron configurations for every element. So try to do it first, then you know, one of these ways, do the electron configuration. Don't know why I'm not getting connection, but anyways, Web Elements is great. I'm just gonna try again. Okay. Anyways, go there. You can, or go to any website. You can find the electron configurations. That's great. Okay. You're back? Great. So now we're going to talk about this one exception. There are 2 energy boosts and drops that we have to worry about. So there's an energy or a stability boost. Stability boost when orbitals are full, or orbital shell. Sorry, let's do an orbital shell. So what I mean is all of the same when okay, we want to say degenerate orbitals are all equally full. So this is a tricky statement. I chose it very carefully. There's a stability boost when degenerate orbitals are all equally full. So for example, if we did a 3p orbital, 1, 2, 3, there's 3 different ones, right? This is your, you know, I want to keep reminding us of what's going on here. So here's your, this is N, this is L, and then we have ML here, and there's -1, 0, and 1. And so we have this setup. Make a couple of these. So when we go to add electrons to this setup, if we have an electron here and here, this is, you know, it's whatever energy. But when you half fill it like this here, so in this example, in the first example, the 3 orbitals are not equal. They're not equally full. But if we had 3 electrons, then they are equally full. So this is not equally full, and this is equally full. So if we put a little energy scale here, like this, what we're trying to say is that these ones would kind of drop down. There'd be a little tiny drop. And then what's weird is if you added the next electron or whatever, so, you know, even if you went to this many electrons, the orbitals would stay where they were, or even because you now have some electrons that are half filled and some that are full, they might actually pop up a little bit. So maybe I should do that on this other one. So if you only have some that are partially full, they actually will drift upwards a little bit, just a little tiny bit, but enough to make it less likely than some of the other examples. And then the other way, of course, the other way to have equally full is to have true fullness. And so I'm just going to get this one over here. And this one will be even slightly more full, more stable, to have all 6 electrons. So equally full. This one is also equally full. full, and extra stable. Extra stable. Maybe call it complete fullness. All right. So this is the idea. Now this makes some interesting stuff happen. I just want to kind of remind ourselves of what we're doing here. So we're saying that we've got sort of almost 3 different energy. We have 4 different energy levels here. All right, so this means that in some cases, you could actually cause some really interesting effects to happen if you're very, very careful with your electrons. So let's look at the 4s and 3d orbitals. So the 4s orbital has some energy. We're going to again put our little energy symbol here. And the 3d orbital is technically a little bit higher in energy. Okay. So I'm going to put my little orbitals here. Lines. Okay. But so this is our starting point. I feel like I'm gonna regret making it so big, so I'm gonna do a little shrinking here. Okay. But if you had the same setup, all right, I'll just move everything down here. Because the 4s and the 3p are so close, if we had something like, let's do zinc, for example, then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have all of these electrons, and so you can think that these will actually drop down. And they might even drop down to the point where they're kind of on the same line. In fact, what we actually do find is that these actually even drop down even a little bit lower, and they become very, very stable, very difficult to do any chemistry with. And that's why the 4s orbital is so much more reactive. Or another reason why the 4s orbital is reactive. Okay, so let's put them right here. Well, now this is an interesting quandary, because if you start with this original setup, copy, and I'm going to put a new setup over here. If we start with this, and we're going to duplicate that, make it a second one. If we started with the same setup, but what if we had 2 electrons? What if we put 2 electrons here, and we put 1, 2, 3, 4 electrons? So say like chromium. Is that chromium? Let me just look. Yeah, chromium. So this is the case with chromium. Well, if you had this same setup, but you were able to move one of those electrons up, you might do that kind of thing. And now all of the electrons are equal. It's actually now kind of almost like you have a 4s and 3d are kind of the same orbital. And I don't know if the energies are exactly the same, but you do get that drop by having that half filled, right? You get this equally filled, equal filling equals energy drop. So equal filled 3d5 equals energy drop. And so this is why you'll find that for chromium, chromium will be 4s1 3d10. Copper, I believe, is the other one. Yeah, copper is copper will be 4s1 3d10. Sorry, 3d5. 3d5. Right, so this is 5, 1, this is 2, 4. Anything that has any of the 4D elements, so let's go back to our little picture here. Any of these ones right here, I'm going to use a different color now that we've covered this. Any of these and any of these elements will be, any of these ones will be capable of this promotion. So these will be D5 as well. So the S1D5, S1D10. So they promote a single electron. There is, I think, one other example, I think is palladium, where 2 electrons are transferred for whatever reason, some weird combination of energy levels. But in general, if you can make one promotion and it equally fills the orbitals, then that is likely to happen. If moving one and only one, I saw someone earlier and they were moving 2 electrons, and we had a discussion about it, and they were like, they realized what was happening. If moving 1 electron allows for a half or full D subshell, then this likely happens. Okay, so there you go. That's what used to be called an exception. I don't approve of it called an exception. It's just more information you didn't have. I don't know if that's the definition of an exception, maybe, but that's the idea. All right, that gives you everything. Just get out there, write out electron configurations, study them, get into them, just play with them. They're really interesting. There's lots of cool stuff once you figure out what's going on the periodic table and how these electron configuration changes. If you can get this connection of what is going on in these N's and L's and how they're changing across this periodic table, you'll have a lot more interesting things you can do later relative to chemistry.